Parallelizing brute force traveling salesman. Problem using OpenMP. In this video, we present our project where we discuss our attempts at parallelizing the traveling salesman problem, also known as TSP, our experiments using OpenMP in C++, and our results. But what is the traveling salesman problem? The traveling salesman problem, TSP, is a long-studied algorithmic problem that aims to calculate the shortest possible route that can be taken to visit several given cities, each exactly once, and return to the initial location. Since TSP is an NP-hard problem, meaning that the execution time grows exponentially as the number of cities increases, it requires an efficient, cost-effective, and scalable solution. In this project, we asked ChatGPT to generate an unoptimized C++ code that includes more than one independent loops, if conditions, and heavy computation that increases in complexity with the input size, which can all be used to experiment with parallelization. So, what makes our problem suitable for parallelization? First, independent loops. We make the same operations with different numbers repeatedly, so this allows us to apply parallelization inside the loops, since we can calculate them independently. Secondly, calculation of repetitive distance. We can parallelize the function that solves the traveling salesman problem by allowing threads to compute the route distance for different cities, since it contains many recalculations. Lastly, usage of the brute force approach. We used a brute force approach to solve TSP. In this approach, all the possible permutations of city routes are generated. It calculates and compares all the permutations to achieve the shortest route, which can be time-consuming when executed sequentially. Sequential benchmark. The sequential code calculates the optimal route for 12 cities, the recorded execution time being 634.441 seconds, which is approximately 10 minutes. This measurement provides a baseline for parallel computing techniques. Parallel benchmark. The three approaches used for race condition-free parallel code are critical sections, which are used to protect shared data enclosed within a block, atomic updates, which are used for specific memory updates on individual variables, such as incrementation, and reduction, which performs local computations on a shared variable and combines their results at the end. Finally, the results. From the table, we can see that atomic is generally faster than the other options, which could potentially make it the best choice. However, there was one shared variable in the code that couldn't be handled due to it being a complex calculation. Therefore, it isn't the most optimal option, since race conditions are still possible. This, in our opinion, makes reduction the best way to handle the shared variables in our code, as its execution time is rapidly decreasing as the number of cores increase. Through these findings, we contribute our perspective on applying parallel computing to optimization problems and prove that parallel computing significantly reduces computation time while maintaining solution accuracy, confirming that parallelization is an effective approach for handling the TSP's computational challenges. Thank you for listening.